So now we are now on lesson 10, titled Newton's Laws of Motion. I think most of us are already familiar with these laws. I think they were introduced to you possibly in grade 11. So I believe that it's a good idea to start here before we actually get into work. It's important for us to start with Newton's laws of motions. And as always, our learning objectives for this lesson is that at least by the end of this lesson, you should be able to state all Newton's laws of motion. No, there's three of them. There's Newton's first law of motion, Newton's second law of motion, and Newton's third law of motion. And then another important thing that is normally asked in your question papers is you have to be able to explain why safety belts, it looks like an H, the safety belts are an important feature in cars. So, without wasting any time, let us just get straight into it. So, as we know, Newton's first law of motion states that an object continues in a state of rest, in a state of rest or uniform. So when we say something is moving with a uniform velocity, we mean that it is moving with a constant velocity, unless it is acted upon by an unbalanced, or maybe somebody might say net or resultant force. So what does this mean? So Newton's first law of motion is due to something called inertia. And we're going to define what inertia is shortly. So inertia actually refers to the resistance of an object to change its state of rest or constant or uniform motion. So these two, it's important for you to be able to define what is inertia, as well as you should be able to state Newton's first law of motions. But what are the implications of Newton's first law of motion? So remember, for Newton's first law, we are concerned with objects that are either at rest or stationary. If something is at rest or it's stationary, we know that its velocity is 0 meters per second. Or objects that are moving at a constant or uniform velocity. So this means that the change in v is 0 meters per second, because Vf and Vi are equal. So the initial velocity of that object. So imagine that you had a car that was moving on a path. So here it had an initial velocity of 10, and then maybe after a couple of minutes the car is now here and it still has a velocity of 10. So there's 10 meters per second, 10 meters per second to the right. So if we were to calculate the change in V, then you say Vf minus Vi, which will be 10 minus 10, which is nothing but 0. So normally this is in Newton's first law, we are concerned with objects that are at rest or moving at a constant or uniform velocity. But then what does this mean? So we know that acceleration of any object is given by a change in V over the time interval. So if the change in V is 0, doesn't matter what the time is, it can be 5, this acceleration will be 0 meters per second squared. Or so you see that. So this means that if we now kind of go a little bit further, we haven't talked about Newton's second law, and we know that Newton's second law says that the product of mass and acceleration will give us the net force. So if acceleration is 0, this entire thing on your right hand side would be equals to 0. So this means that F net will be 0. So there would not be any resultant force acting upon that object. Another important thing, especially with respect to Newton's first law, that they like asking, they would normally ask you, why is it important for a person to wear a safety belt when they are in a car. I'm going to try to draw a person. So let's say this is the seat of a car, and there you are sitting there, and then you are wearing, so this is like a safety belt. Yeah, imagine this to be a safety belt. So why is it important for you to wear a safety belt in a car? So according to Newton's first law of motion, it says that an object will remain at a constant velocity or unless a non-zero force or a resultant force acts upon it. And then when a car is in an accident, so now imagine maybe your car is, so this is you in a car, and then you come across this wall and you're about to hit it. So immediately the car will come to a sudden stop. But then the person inside, unfortunately, even if the car stops, the person inside still continues to move with that constant velocity because of inertia. Remember that resistance to change its state of rest. So you as the person will continue to move forward with a constant velocity. So without this safety belt, you're gonna find yourself now crashing into this windshield. I know it's a terrible looking car, not windshield, crashing into the windscreen of the car, causing perhaps a very severe head trauma. So now what the safety belt does is that it will act as a sort of an applied force, preventing you from actually now hitting the windscreen. So that is normally how you would answer a question like that. And then another thing, when they describe inertia, they like doing an example whereby you have maybe imagine you have a glass of water, and then you have a piece of paper on top of it. I hope that is clear. And then because objects will normally resist to so object they resist to change their state of rest. So if I pull this, I hope it works. If I pull the paper, this coin is gonna fall inside it because the coin is not gonna move even though the paper moves. So you see, that's why the coin actually falls inside the glass, because of that inertia. Even though the paper moved, the coin remained in its state of rest. So yeah, I think now let us move on to Newton's second law of motion. So, Newton's second law of motion says that when a net force is applied to an object with a mass, it accelerates. So, keyword there is net force. It accelerates in the direction of the net force. And then they say that the acceleration is directly proportional. So, in previous videos, we have actually described what direct proportion means to the net force and inversely proportional to the mass. So what does this mean? So in mathematical terms, Newton's second law of motion is given by F net. This is an equation that you're quite familiar with. F net equals to the product of mass and acceleration. So we have F net equals to the product of mass, it's in kilograms, and acceleration in meters per second squared. And what is it that they say? So imagine you have an object and you have various forces acting on it. Maybe we'll have the normal force. We're still going to talk about the different types of forces. So maybe you have the normal force, maybe you have frictional forces, maybe then you have an applied force. So they're saying that if we add the effects of all of these forces, so we would have maybe frictional forces plus, okay, that doesn't make sense because the normal force is in the y direction, so let me not include it. And then you have your applied force, and all of that will actually be equals to ma. So you have to add all their individual effects. And so it's like the vector sum of all the forces acting on the object. So now let us explain the effect of Newton's second law on overloading. So imagine a car that is overloaded. What is the effect of Newton's second law of motion? But before we go that, it's important to know that, remember in Newton's first law, F net was equals to 0 newtons. Why? Because the resultant force, the total net force, was 0, because A was 0 meters per second squared. But for Newton's second law, it is equals to ma, and acceleration. So you'd actually have an accelerating object. So acceleration is not equals to 0 meters per second squared. So meaning we actually have a changing velocity. So if we have an object there, a car, and then after a certain while it's there, maybe vi was 5 and then now vf is I'm not sure, 10. So the change in f, the change in v, I apologize, the change in v will actually be just 10 minus 5, which is 5. So this will mean that in this equation over here, the change in v would be 5. That's why you actually have a car or an object that is accelerating with Newton's second law of motion. But now, like I mentioned, what is the effect of Newton's second law on overloading? So this is just something important for you to know. So if your car is overloaded, the stopping distance will increase. So let's say here you are and you've overloaded your car with loads of potatoes there, and then you try to apply the brakes so that you can stop. That distance will actually be increased. It will be difficult for you to stop quicker. So imagine you have a car here that is just heading towards you and you want to stop here, but because you are overloaded, that distance is actually going to be increased. Maybe you might brake here, or after you've actually come in contact and collided with this oncoming car, and this will actually cause serious accidents. So when you apply those brakes in your car, so the force, which is friction, that is remains the same, but the increase in mass causes a decrease in the negative acceleration. So remember, when you apply brakes, you actually, now your net force will actually be in the opposite direction because you're trying to brake as well as your acceleration. So your if we said to the right was positive and to the left was negative, so your net force will now be in this direction, and then even your acceleration will be in this direction, so it will be negative as well. And increasing the time and distance it takes for this vehicle to stop. So that is just something that is quite important for you to know if you are asked a question about the effect of Newton's second law on overloading. So Newton's third law of motion says when object A exerts a force on object B, so we have two objects A and B, object B simultaneously exert an oppositely directed force of equal magnitude on object B. So you have two objects there that they are exerting a force on each other. So we have the force of A on B, which will be equal to the force on B, the force that B exerts on A, and the only difference will be their direction. So this one will be negative and the other one will be positive. And we call these forces action-reaction pairs. Wait, action-reaction force pairs. And there are a few properties that they have, all of them in common. The first thing is that the forces that they exert on each other will be equal in magnitude. So if this one exerted a force of 10, this one will also exert a force of 10 in magnitude, 10 newtons. But the only difference will just be the direction. So this will be negative 10 newtons. And the second thing is that they act in opposite directions. So this one will act in this direction and this one will act in a different direction. And they act on different objects, so they do not cancel each other out. So that is an important thing to know. So we can make an example about an action-reaction pair force. So an example would then be, imagine there you are on your skateboard, and then there you will exert a force on the wall. So this will be your force of this guy here on the wall, and then the wall will also exert a force on you, the same magnitude but opposite in direction. And Newton's third law says, so imagine if you have two cars, there's a small Vrupa there and a huge truck, and they're about to collide. These two cars will actually exert the same amount of force on each other, irrespective of their masses. And this brings us to the end of this lesson. So on Newton's laws of motion, we're still going to talk a lot about forces and eventually do calculations. So I hope you're able to follow up this lesson. And yes.